This is the Graph on Robotics talk series. My name is Vilen Jairam, and I'm a faculty host for this talk. And as a quick reminder, previously recorded talks and series can be found on our YouTube channel and website. If you're joining us via Zoom, please submit your questions using the Q&A button at the bottom of your screen, and we'll answer them during the Q&A panel at the end of the talk. If you're here in person, you'll have an opportunity at the end of the talk to provide your questions to the panelists, and we'll have a 15-minute or so Q&A session at the end. Okay? Our panelists today are Edward Hu and Fernando Pereira, who are both fifth-year PhD students. Edward Hu works with me on robot learning, and Fernando works with Anishay and CJ Taylor and Vijay Kumar. So we're really fortunate today to have Professor Zach Kassas as our speaker. Zach is the TRC Endo Chair in Intelligent Transportation Systems and a professor in the Department of Electrical and Computer Engineering at The Ohio State University. He's the director of the Autonomous Systems Perception, Intelligence, and Navigation Lab. The research interests include navigation systems, low Earth orbit satellites, cognitive sensing, software-defined radio, intelligent transportation systems, autonomous vehicles, cyber-physical systems, so really a broad gamut of things, right? And he's also the director of the US Department of Transportation Center, the Center for Automated Vehicle Research with Multimodal Assured Navigation, or CARMEN. It focuses on navigation resiliency and security of highly automated systems. So Zach received his PhD in electrical engineering at UT Austin in 2014, after having received 2 master's degrees prior to that. And within 8 years of the PhD, Zach was already a full professor, and then within 10 years, he is now an IEEE fellow, besides being a distinguished lecturer of the IEEE Electronic Systems Society. Really a very formidable list of accomplishments. I think this is a strong testament to the quality and impact of his work. If I read off all his awards, it would take many more minutes, so I won't keep you for that long. I first met Zach at an NSF workshop about a year ago, and I heard about the incredibly cool work that his lab was doing, and I knew immediately that I wanted more of us here at Penn to hear about it. I'm glad that that has also percolated through to you. I wish that more people will also be able to view the recordings and also on Zoom. Right? So I'm very glad that now, after about a year, we've managed to finally bring Zach to Penn to give us a talk about his really cool work. With that, Zach, whenever you're ready, please take it away.
All right. Thank you so much, Dinesh, for the very nice introduction. And indeed, it was about a year ago when we met, and I also enjoyed your work, and it's mutual. I invited you to Ohio State earlier, and I think as a testament for the impact of your talk, I was telling my students I'm not going to have a lecture today because, or sorry, I should say yesterday, because I'll be traveling to Penn. And then someone said, Penn, we had a speaker from Penn a couple months ago. Are you going to see him? That talk was the most awesome talk I had seen in all of our seminar series. So I was like, I got to tell Dinesh that. So yeah, so it's a pleasure being here. And before I start, because this is also offered apart from the being a seminar, it's offered as an IEEE Aerospace and Electronic Systems Society distinguished lecture. So a little bit to tell you about AESS. I have just a couple slides just to overview what we are. It may be misleading because of the name, but it is pretty much a society that has to do with organization, system engineering, design, development, integration, and operation of complex systems for space, air, ocean, or ground environments. So if you're dealing with things like navigation, avionics, mobile electric power and electronics, radar, sonar, telemetry, military, law enforcement, automatic tests, simulators, and command and control, you actually have a place in the society. It's not very dedicated like certain societies in IEEE. It has a pretty broad reach, and it's more of a systems society. So don't let aerospace and the name mislead you, because it is beyond just space systems. And what I will show you is several applications beyond space systems. So like other IEEE societies, they have their own conferences, publications, technical panels, and this is a snippet of the conferences that they have: radar conference, aerospace conference. There is also a position, location, and navigation symposium. So if you're doing things in navigation, I do encourage you to think about it. It will be in Salt Lake City next April 2025, and I happen to be one of the organizers of that conference called PLANS. In fact, there is a session for robotics there. And then their flagship journal is Transactions on Aerospace and Electronic Systems and Aerospace and Electronic Systems magazine. And they have other co-sponsored journals like Systems, Journal on Systems Engineering and Transactions of Radar. So this is something that a lot of people don't know. If you go to their website, there are more than 100 distinguished lectures recorded and posted there. And I can assure you, no matter what your interest is, there will be a topic for you to learn from. So those are from pioneers in their fields. I'm supposed to give this online in a few weeks. It will be a different version than what you will see here. You know, I saved some cool stuff for you, but I encourage you to go and check it out. It's really a wealth of information. I keep sending my students, you know, as they go through their studies, oh, there is this topic, there is that topic. So a lot of also estimation topics and target tracking are posted there. There are also several technical panels you can see from there, you know, the broad scope, and then about more than 6,000 members in the society. This is a new initiative that started. I think, you know, I like this slide because it could relate to some of what you are doing. It's a 3-year initiative for underrepresented regions, and it's expected to grow technical capabilities. There is a focus on radar, electro-optical sensors, and data fusion. So you can also check it out. And with that, I will first and foremost, I would like to thank my students, past and current. This is just a snippet of the students that had a hand one way or another to the slides that I will show you. Without them, you will not see any of this. So I really appreciate their hard work and letting you see the fruits of their labor, as they say. So let me start, you know, we will have lunch after this, shortly after. So I used to live in Texas, and tacos is one of my favorite food. I know we will have pizza here. We are on the East Coast, so it's different. But let's imagine our lunch will be delivered by a taco drone. And of course, it will not be Taco Bell unless you are a fan of that, but I do not recommend it at all. So order your lunch. It comes with a taco and a taco drone. And let me show you the state of technology today, right? So the state of technology is the drone flies to your location to deliver the taco before it gets soggy, right? You don't want to eat a soggy taco. As it flies, imagine there is a failure in the navigation system. So the navigation system on board these drones is composed of a GPS or a GNSS, Global Navigation Satellite System, coupled with an inertial navigation system. Let's imagine the GPS receiver fails for one reason or another. Now you're only navigating based on the INS, the inertial, or the IMU specifically, the inertial measurement unit, which accumulates errors, and the drone gets lost. It doesn't know where it is. It's basically, in control language, it's an unstable system. It flies over that crowded city, flies over this power substation, tangles on the power lines, and falls in. So if you think this is sci-fi, I would tell you no, it's not. It actually happened to us, unfortunately. This is our drone. After it crashed, we were not delivering a taco. Ironically, we were looking at an alternative navigation system that I will talk about in a second. But as my students were searching for the drone, they talked to a security guard. I said, yeah, I saw something fly in the sky, and I took a video. There you go. That's the drone flying before it did tumble on the power lines and crash. So basically what this is telling us, we need improved fall detection, isolation, and recovery. We need a backup navigation system, and we need to secure the critical infrastructure. So this is really not a new issue. In fact, for the past several years, we've been getting warned more and more from several organizations, including the International Civil Aviation Organization, that had this technical commission memorandum asking for alternatives or backups to GPS and to protecting the GPS band from interference. And I will talk more about those issues recently. That happened recently. So this is from back in 2019. They followed with another one. And then the US Department of Transportation, the Volpe Center in 2021 had the complementary PNT, which stands for Positioning, Navigation, and Timing, and GPS Backup Technology Demonstration Report. Then NIST in 2021 had their foundational PNT profile, how you can apply cybersecurity for PNT services. Then there was a another memorandum by the International Telecommunication Union in 2022. And then more recently, the FAA issued a warning because of these interferences. Now, with our drone, we don't know what happened, whether it was interference or a failure. We know that GPS failed. And when we recovered the drone, it said there was no GPS signals being received. So historically speaking, over the past decade or so, if you are in the navigation field, radio navigation specifically, you will realize that GPS interference has historically been a military or an academic concern. Recent conflicts around the world have affected civilian systems and is really a concern for everyone. So September 2023 was the first case of GPS spoofing impacting commercial aircraft. So this is, I would say, a historical date because in 2024, that bubble burst. And this is just a snippet of story that's really now mainstream media talking about how GPS is being impacted because of jamming and or spoofing around the world. It's grounding aircraft, it's shutting down certain airports, it's diverting planes, so it is really a big, big concern. So that's for aviation, and of course, there are a lot of concerns for the average Joe, who's carrying his phone, trying to navigate, not knowing where he or she is, or if you have a self-driving car or a drone, and. So you can extrapolate. But of course, planes, we take them, it's a safety critical system. So this is why, the focus there or the damage there could be severe. So for those of you of a certain age, I don't know how many will recognize this, but if you do, kudos to you. This is from the X-Files. The truth is out there. So what I'm trying to say here, even though GPS or GNSS monopolized the navigation truth for so many years, right? We depend on it so much. There are other versions of truth. And those truths in the community are called signals of opportunity. So they could be terrestrial, right? AM, FM, Wi-Fi, DTV, cellular, or they could be non-terrestrial, maybe satellites in low Earth orbit. Now, these signals of opportunity or sources, whether terrestrial or non-terrestrial, as you can guess, are not intended for you to navigate with, but rather they're intended for communications purposes. The idea is, can you exploit them for navigation so you don't have to design a new system like GPS, which also will suffer from vulnerabilities, right? So that's the idea here, is can we do that? So there, if you are interested in this, there was an entire book from chapter 35 through 43, every chapter dedicated for one particular flavor of these signals. You can check it out. I happen to have had the honor to write 2 chapters, one on cellular and one on low Earth orbit. So you can check that out. But the way I like to approach this navigation with signals of opportunity, being in the GRASP lab, you're probably intimately familiar with SLAM. I think of this as a radio SLAM problem, and that's how, what I started looking at in my PhD. How can I formulate this problem as a radio SLAM? So the way to understand it, let's start with a traditional navigation system. You have a GPS receiver, you have GPS satellites. You get measurements from GPS satellites, you use them to estimate your state, usually position, velocity, and time. You don't care about the states of the satellites because they tell you their states. They tell you their position, they tell you also their time error. Okay. Now imagine you have one of those terrestrial transmitters in the environment. Let's say it doesn't move, right? So its state is its position and clock errors, bias and drift. And you make some nonlinear measurements corrupted by measurement noise on that transmitter. If you don't know where it is, then you think of it as a SLAM problem or radio SLAM, in which case, not only you have to estimate your states, but now you have to estimate the states of that terrestrial signals of opportunity. And this process of on-the-fly signal characterization and estimation of different sources, whether terrestrial or non-terrestrial, have to take place. Now, one difference between SLAM and radio SLAM is that the signal landscape that you are building is a spatiotemporal map, right? The state space is not stationary. So metaphorically speaking, it's like a jello. And the firmness of that jello is a function of how stable the clocks or the oscillators on board these transmitters. So imagine you have a relatively stable clock oscillator, that is used to generate the signals on board of these transmitters, then the jello, this is typically they refer to these as OCXOs, oven-controlled crystal oscillators, then the jello you are building looks like this firm jello. If you have a lousy clock, something like what you have in your phone, for example, TCXO, temperature compensated crystal oscillator, then the map, your radio slam map, looks like this. Now, if you have satellites, it gets even more fun. Then this is the kind of map that you are building, like flying jello. Okay, so that's the idea. I'll not go through this, but we've published several papers over the years, starting with observability analysis. What do you need to have radio slam problem even observable? I would stress the last paper if you are interested in motion planning or in active sensing, because this shows you the importance of active sensing so your estimate of yourself and the map doesn't diverge. Actually, if you do not plan your trajectory, then your estimator will diverge. So the last paper is really interesting because also it tells you the best trajectory to take from the UAV's origin to a waypoint is not a straight line. You have to make some very funky trajectories. And that can be a talk by itself, but Dinesh said he would like to hear more about my LEO work, so I will focus on that. But before going to LEO, let me show you what we can do on Earth, because there is a lot of cool things we can accomplish before I take you up to space. So this is the radio slam block diagram. I'll not go through the details. Each one of those slides could be a talk by itself. But the big picture is you have an inertial navigation system. You have your signal of opportunity receiver, and then you are tightly coupling your INS measurements with the inertial, with the signal of opportunity receiver measurements via an extended Kalman filter or any filter that you want, right? So there is a prediction correction step that's happening, and this is what you are doing. The challenge is you have to estimate this very, very long state vector, which is composed of the IMU states, so the quaternion, position, velocity, gyro bias, accelerometer bias. You have to estimate your timing error. You have to estimate every transmitter's position and its timing error. And it keeps growing and growing and growing. So those are the states that you estimate. This paper talks about everything that you need to set up this problem and what you can and cannot achieve. This paper talks about some stochastic observability considerations because the timing error is a dynamic stochastic system. So that tells you how you can ensure that your uncertainty doesn't drift indefinitely over time and how you can assure that it remains bounded. Okay, so let me show you some cool stuff with what you can do with this. For now, let me assume I know where the transmitters are, but I will estimate their timing error. Their timing error still makes the problem radio slam because you are estimating, dynamic and stochastic states that represent the timing error of every transmitter. So we are not the only research group working on cellular-based navigation. So this is from several years ago, actually 2019 to be specific, where we achieved, and up until now, to my knowledge, it's still the record of the most accurate non-cooperative cellular-based navigation on a UAV, sub-meter level. So this UAV that you're seeing here traveled over the trajectory you are seeing. So basically, the blue is the ground truth trajectory, and the red is what we are able to estimate simply by listening to cellular LTE towers in the environment, fused with altimeter data, so you can see how accurately we can navigate that drone. Okay, so as I said, it's less than a meter. So the total trajectory was 605 meters, and then our 2D and 3D position RMSE was less than a meter.
Seems like the timing errors are static.
No, we estimate them dynamically over time. And the locations, yeah, if they are cellular transmitters, they are static. What we are also doing here, as I said, each one of those can be a talk by itself. What we are doing here, we are exploiting the loose network timing synchronization of cellular towers to be able to get this sub-meter level. because the cellular network is loosely synchronized within a microsecond or so, or on the order of microseconds. Okay, so actually this is our friend Johan, that we call the drone Johan, before he flew away. And this is actually the time when he took off and we couldn't recover him. So that's my student Ali setting the drone to flight. And the idea was to fly and redo the same experiment, but with 5G, right? And you can see here at one point, it disengaged from the controller, and it tells it disengaged, and it took off. And then you can see the student starting to run after it, but you can't catch it. But interestingly enough, after we recovered the drone, we had another redundant navigation system that's simply logging. And that's how we knew how the drone flew. That's in red. Simultaneously, our system kept recording signals from the 2 5G towers back in the park. And when we processed them through our receiver, we managed to get a very good estimate of the drone's trajectory with only two transmitters. And actually, it flew for more than a kilometer before crashing. You can see here. Okay. So then we got a question, or I got a question, multiple times. Can you do this on high altitude aircraft? And I took this as a challenge. I think it's fun. I think research should be fun. Otherwise, I don't think you should be doing it. So I thought, okay, well, this sounds fun. Let's do it. So I collaborated with the US Air Force. And this is the badge that the pilots wore. They called their flight campaign Sniffer, which stands for Signals of Opportunity Navigation in Frequency Forbidden Environments. Kind of like a cool name. But the idea is, can we do this? And how high can we navigate on an aircraft? So we took our best receiver to date, put it on the aircraft, collected signals, and then we saw, can we even track? And we were surprised. We got about a dozen or so towers that we can listen to. But as we went higher and higher, those signals got weaker and weaker, and then we couldn't see anything. So I will not go through the details. My brilliant student designed a completely new receiver design that is very different than what you have in your phone, that essentially takes advantage of the OFDM nature, the orthogonal frequency division multiplexing nature of the sequences that are transmitted by 5G to create a very, very long sequence that has nice correlation properties. I can point you to the paper if you are interested, but the punchline is we went from about a dozen or so towers that you can see here. So I would warn you not to blink, because this is how many towers we could track, all the way to about 23,000 feet above ground level. We didn't fly higher than that. I suspect we will still get something decent higher than that. And some of the towers were more than 100 kilometers away from us. So this work was recently featured on the cover of Inside GNSS magazine and in IEEE Spectrum. So let me, we called it Protecting the Skies. So this is radio slam on one flight trajectory. You can see here, this is not your short trajectory. This is a total trajectory of tens of kilometers. I'll show you some the table in a second. But this is the initial uncertainty here down here that we have on the tower. We have some uncertainty. We initialize our radio slam, and then we converge to this yellow pin. If you look where we converged, actually, we converged to this blue pin, and this is the 99th percentile uncertainty ellipse. And then if you look at the yellow pin, there are some antennas on this water tank in the middle of the desert. So we were able to use all these towers and navigate our aircraft. Well, how well can we do? So for this particular trajectory, 56.7 kilometer in length with no GPS, 8.5 minutes flight. So if you know where the towers are, you are estimating their timing error, but you know where they are, you can navigate with a position root mean squared error of 10.14 meters. That's pretty decent, no GPS. Now, if you are doing radio slam, so you don't know any of them, then you degrade to about 43 meters, which is still decent, right? And if you know 2 and you are estimating 4, then you are somewhere in between, 28.2 meters. Okay, now, if you do the active perception which I have pioneers and the audience about, motion planning, trajectory optimization, those numbers get better. But we didn't have that capability to tell the pilots, do this, so you get better. This is just open loop. Okay, let me show you a video of the sniffer flight campaign. So those are the pilots that flew the aircraft. They call her Miss Mabel. So that's the C-12 aircraft. And then you see some of the antennas. Actually, the cellular antennas were mounted at the bottom of the aircraft. This is the RF rack that my students assembled in my lab, shipped it to the Air Force Base, installed it on the aircraft, and took off. So they flew for about a week over different regions in Southern California, urban, semi-urban, and rural, basically to see how the performance would be in various regions. You see here the various regions. They revisited the same region also to see repeatability of the experiment. Nevertheless, this is here how accurately we can estimate the aircraft. So that's the ground truth. They gave us the ground truth. They said, this is how we flew. And then we told them, okay, let me tell you how you flew. And we ran this through our receiver, then our navigation filter, which was this tightly coupled extended common filter based. And that's what we got. So let me zoom in to another flight. That's another flight trajectory. I think here you will see radio slam in action. Let's see here. Is it somewhere here? Maybe before. Oh, there you go. I like this one. So this is, we detect that there is a transmitter in the environment. We map it. That's our estimate. Very, very close to the tower, and that's our uncertainty. So another tower in the middle of the desert. Good. Good. That's a data association problem. We are not doing it as sophisticated as a data association filter. Turns out that every tower transmits a unique ID. If we decode that ID, cell ID, they call it. It is. But then, that's the next research question. Yeah. Good question, Dinesh. Yeah. So, but if you don't, then you have to do a data association problem and match. So I like this maneuver. So we thought that they are landing earlier than we agreed. Next thing you know, they are coming back to the runway, but they did what they call a touch and go. They are just, I guess, having fun. Touch and go. And look at our estimate all the way following the aircraft on the runway and up again. So now let me take you to space. This is the main dish. This is what Dinesh wants me to talk about. So navigation with Megaconstellation LEO satellites. So for those of you that are not, into the navigation world, we think we live in the GNSS era, global navigation satellite systems. GPS is the American system. There is GLONASS, a Russian system. There is Beidou, the Chinese system. And then there is Galileo, the European system. And as I said earlier, these systems monopolize the truth of navigation. We rely on them to navigate. However, the good news is those constellations are getting new friends in low Earth orbit. Starlink being the granddaddy of all. Then you have OneWeb, Iridium, Orbcomm, and the list goes on and on. There is a lot of excitement and hype in space. So this is why I said Starlink is the granddaddy of all. As of last month, there were about 6,200 Starlink satellites in low Earth orbit. When it's all said and done, they want to go up to about 30,000. And you see others. OneWeb, currently 648. They want to go to 882. And of course, your friend Bezos doesn't want to be left behind. So he's creating his Amazon Kuiper constellation of about 3,000 satellites or so. So it is exciting times for connectivity, worldwide connectivity. But as you can imagine, these satellites will offer us a lot of opportunities for navigation. So why there is a big hype now in the navigation world called LEO PNT, LEO positioning, navigation, and timing. So why? First of all, the satellites are much closer to Earth. So GNSS satellites are 20,000 kilometers away from Earth. These are about 1,000 kilometers. So you will get much stronger signals from them. And in fact, we experienced signals more than 20 dBs higher than what you get from GNSS. So, jamming these signals become not impossible, but harder. Also abundant. So I can't keep up updating this slide, so I gave up. In 2019, there were about 2,200 LEO satellites. In 2029, they're predicting that to go up to 57,000. And this is very conservative. This will just be way, way more. I mean, you can tell Starlink by itself will dominate for the time being. They are placed in geometrically diverse orbit. So this is great for something called dilution of precision. And then finally, they are transmitting in a broad swath of the spectrum. I will show you results later in the VHF band, L band, all the way to the KU band. So basically, right now, GNSS are in the L band. It's a very narrow band. You jam it or spoof it, you're done. Whereas now you're making it harder. You have multiple sensing modalities, and grasp lab, maybe terminology. And you don't have to pay anything. And I'll show you why. You don't have to even build new constellation or new infrastructure, because I'm going to exploit these similar to how I exploited the cellular infrastructure. There are three schools of thought for LEO PNT, for LEO-based navigation. The first tells you, let's design dedicated constellation for navigation, LEO-based constellations, okay? That's one. The second one says, let's dual purpose the constellation. So it transmits a navigation signal and your favorite YouTube video. So that's what another school. And then there is yours truly's belief, let's be fully opportunistic. So I think of this, this is like the Uber, right? You have cars driving around. Why don't you reuse them instead of installing new taxis, throwing new taxis in the city, or the Airbnb, right? There are some empty rooms, why don't we just host human beings in them instead of building a new hotel? So, it's still, the schools of thought obviously clash. So let's see who will emerge. But let me focus on the fully opportunistic LEO. And one of the reasons why I like it is it gives us a lot of interesting scientific questions. The first two, I'm not so sure about. I may be wrong, some may disagree, but if I'm designing a constellation, there are some nice questions there. But here, what can you do with minimal knowledge, minimal information? How can I reconstruct things? So what are the challenges? What the heck are they transmitting? You're getting a signal. Can you recover something useful from that signal? Some positioning features or timing features that you could use. Where those satellites are, we have a prior. We have actually a very poor prior. But in space language, it's not too bad. The prior you get is from something called two-line element files. They publish those, they update them daily. They degrade over time, and this is why they publish a new file, so they tell you the satellite ephemeris, right? But the errors can grow to several kilometers. In space, as I said, it's pretty empty out there, so that's not too bad. But for our purpose, we want a much better estimate of where the satellites are. They don't put atomic clocks on board the satellite, or these satellites. GNSS satellites have atomic clocks that are so expensive. They put much cheaper clocks, and some of these constellations rely on GPS to synchronize themselves. And also, they are not so tightly synchronized like GPS. So you will have to resolve all of these. And they don't even tell you their timing error. So you will have to estimate their timing error, okay? And finally, there are ionospheric and tropospheric delays that you'll have to deal with. So let me take you with a bit of a journey of how this started. So in September 2021, we announced to the world in the biggest navigation conference that we can position ourselves with Starlink satellites. We basically deciphered enough from the signal, and we managed to position ourselves with Starlink. So this got, a significant attention from science, IEEE Spectrum, and other media outlets. But our first design was a carrier phase tracking based approach. I will not go through the details here, but there is an adaptive Kalman filter, and then there is accumulation, looking at the innovation. We come up also with a good model over a short period of time for the signal change over time. And then you can see here, this is our carrier phase tracking error for six Starlink satellites. And then the red is our, these are, I think, 2 or 3 sigma. Plus and minus 2 or 3 sigma, I forgot, for the errors. So we are tracking the carrier phase from which we can position ourselves. So we started with an initial estimate about 180 kilometers away, and we converged in 3D to about 33.5 meters. using signals from 6 Starlink satellites processed through both our cognitive receiver and through our filter, estimator, position estimator. And the 2D error was about 25.9 meters. So this paper was published in Transactions, Aerospace and Electronic Systems in 2022. And then we went through a heavier machinery based on something called match subspace detection. At a very high level, the way it works is you set it up as a detection problem, a binary hypothesis test. You ask, is there someone transmitting above me? And if there is someone, you estimate their Doppler, you estimate their certain features about the signal, and then you null it. They're all transmitting at the same frequency. So you have to null that source to detect, is there another satellite above me? Usually you detect the most powerful one, then you null it, you project it onto the null space, then you detect the second one. Is there someone else? And it's a sequential process until you exhaust all potential sources above you, okay? I'll not go through the details here, but this is the tracking approach, the blind Doppler tracking approach associated with this method. And ultimately, we got an error here that is smaller than the first. So 22.9 in 3D and then 10 meters in 2D. Okay, and you can see here how accurately we can estimate the Doppler rate. This method suffers from a bias in the Doppler estimate, but that you can add it as a parameter in your Kalman filter and you can estimate it. Okay, so this work got featured inside GNSS, and then the community, the navigation community, liked it so much, from July 2022 through January 2023, it was the most downloaded paper published in Transactions on Aerospace and Electronic Systems. And then more and more people jumped on this, researchers jumped on this, and this group, actually it's my PhD, where I did my PhD in University of Texas at Austin. So they did this fantastic work, and they published more about the signal itself. They said, okay, Starlink transmits these particular sequences called PSS, SSS. This is the period. So they reverse engineered some parts of the signal, and they published it. So that's great. But then we asked ourselves, well, what if Starlink changes their code? So do we go and reverse engineer it every time? And obviously that's something that, and they can do it. Now they are calling them software-defined satellites. They actually have software-defined radio. They can upload a new personality, and change. And they've been doing this. I mean, we know that they've been doing this. Okay, so then we move to, I would say, a much more powerful way of doing things. We call it blind acquisition, tracking, and beacon estimation. This is a LEO-agnostic approach. And the way it works is this idea of the beacon. So think of a pulse, right? A beacon is a periodic signal transmitted for synchronization purposes. Without it, no communication system, to my knowledge, would exist. So you have to have those beacons transmitting. So those are some examples. In 5G, they have OFDM, NOAA satellites transmit AM/FM, Orbcomm, SDQ, PSK, Iridium next, Starlink, OneWeb. Different constellations have different beacons. Now, of course, for 3G, 4G, 5G, the beacon because they tell you, they have to abide by the same protocol. It's published in 3GPP, right? Third Generation Partnership Project. For these are proprietary. So the question is, can we decipher their beacon? Can we detect what beacon they are transmitting? So this idea of paper, I don't know why my student did this, but this just appeared in the Journal on Selected Areas in Communication. It's really a beautiful paper telling you those are the fundamental tracking performance and design considerations based on this idea of the beacon. Okay, so it just came out a few months ago. This is the tracking approach. I will also skip it. We presented this work in last year's PLANS conference in 2023. But we put this idea to test. Okay, we said, okay, let's go after Orbcomm. This is actually the first constellation that we managed to deal with in around 2018. Okay, can we decipher Orbcomm? And we did. Then we went after Iridium. Iridium is another older constellation, and we managed to crack it. Then we went to the KU band. So this is the fun band. This is where Starlink, OneWeb, and Amazon Kuiper will transmit. Can we crack those? We cracked Starlink again, but now using this technique. And then we went after something that hadn't been cracked yet, which is OneWeb. And we cracked it. So by cracking it, I mean, this is our receiver now knows sequences that are being transmitted. If you correlate them with what is coming, you see this pulse train. So this may remind you of your good old DSP days you have taken. So basically, it's telling you, I am correlating, and here, this is a zoom on the cross-correlation function. We are able to estimate the time of flight from the satellite to us. If you know the time of flight, you know the distance. If you have enough satellites with enough distances, you can do trilateration, you know where you are. That's the very high-level idea. So I told my student, as if you have, I'm revealing my age with these gadgets, as if we have this nice radio that you can tune with a knob, and let's see who else is out there. Let's see who else is out there. So let's tune it to the VHF band. So this is why you need to extend it for those of you that don't know. Turns out there is another satellite in the VHF band transmitting, and we are estimating its Doppler. We are estimating its this Doppler shift. This is the Doppler error. This is the carrier to noise ratio. And a new constellation got revealed. So it's the NOAA, the National Oceanic and Atmospheric Administration satellite. So great, let's add it to the mix. And what you are seeing here is how we can track OneWeb, Starlink, Iridium, Orbcomm, and NOAA. And this is our Doppler error, Doppler tracking error, and it's about Hertz level. Okay, great. But can we position ourselves with that? And the answer is thankfully yes. So I told my student, look, we used to be in University of California, Irvine. Let's not change your filter, initial estimate. Let's keep it in Irvine. Now that we are in Columbus, Ohio, can you listen to 2 OneWeb, 1 Iridium, 1 NOAA, 4 Starlink, and 1 Orbcomm? And based on their Doppler, the track Doppler, have the filter converge to where you are. So from 3,600 kilometers away, listening to these, and I showed you the tracking errors earlier, we managed to converge in 3D to about 5.8 meters from where we are. Okay? So then we went back and revisited Starlink. We said, okay, let's see that group from the University of Texas that published the PSS, the SSS. These are primary synchronization, secondary synchronization. Those are the sequences. Can we recover them blindly? And the answer was yes, with 0% error. We managed to converge to the sequences blindly. So basically, that's giving us hope. If Starlink changes, then we can, adapt and cognitively reconstruct. In fact, it turns out that Starlink transmits a lot of signals. What you are seeing here is the first 2 symbols. That's the PSS and the SSS that Starlink transmits. They transmit OFDM signals. And those comprise only 0.66% of what they transmit. So you need this cognitive approach to be able to reconstruct the whole frame, and that's something we just revealed a few weeks ago in the Navigation ION GNSS conference, that this is what Starlink transmits. And why do we care about this? Well, let me show you very quickly. It has advantages in the delay, in the Doppler, and in the carrier to noise ratio. In the delay, you get much narrower resolution. So that allows you for nanosecond level precise code phase tracking. As you increase your bandwidth, look at this up here, you start seeing, look at this resolution you can get. Versus if you have lower bandwidth signal, then your timing resolution gets dilated. In the Doppler domain, you get a narrower main lobe in the Doppler, which allows you for Hertz level precise Doppler tracking. So this is, in red, is the Doppler ambiguity function using just the PSS, SSS that were published. Whereas if you use the full beacon, then you get, look at this spike here. And if you zoom on it, so you get much better resolution in time and in frequency. And my favorite, I like power, right? You get an immediate 18 dB boost. So this is the carrier to noise ratio with PSS, SSS. you immediately get, when you use the full beacon, you get an 18 dB boost. So you may ask why? Why do you like this? Well, so this paper was just published a couple of weeks ago. The reason why I like this is I was thinking, okay, let's do something fun with Starlink instead of just the stationary antenna. Let's fly, right? So showed you our drone flying, so maybe we can fly a drone with this. Then maybe drones are a bit boring, especially these days. Can we fly something higher, maybe urban air mobility? There is a lot of hype about it right now. So maybe something as high as the tallest man-made structure, Burj Khalifa in Dubai. Maybe fly even higher, at closer to Mount Everest, the tallest God-made structure. Can we fly that sniffer campaign, at cruising altitude of aircraft with Starlink? So that's 11,000 meters. Can we even go higher? This is the SR-71 Blackbird, 26,000 meters. So we started running out of ideas. How do we show why this 18 dB boost is important? And I'll tell you in a second why. But we ran out of ideas, and we thought, okay, let's open the Greek mythology books. And then we came across Icarus. So it was like, okay, what's up with Icarus? Well, it turns out that Icarus was trying to escape from the island of Crete. And his father told him, don't fly so high, close to the sun. Your wings made of feather and clay will melt, and you will fall to your death. And Icarus, being young and stupid, I should say, and ambitious, he didn't care. He did fly, and he went, fell to his death. So the idea is that didn't deter us. We were still, as they say, stay young, stay stupid. So we were like, okay, let's fly as high as we can. Okay, so the issue is, if you start going to these heights, you will be confined to how much payload you can carry. It's not an aircraft, and probably you'll guess what we ended up flying. You have to rely on these called low noise blocks. It's a small antenna this big. Now, before 2023, Starlink were transmitting powerful pilot tone signals that we can detect with those LMBs. After 2023, we call it the dark ages, they toned down their signal. And you cannot detect those anymore. You need a big dish. You need a big dish. So we cannot have Icarus fly with a big dish. We have to rely on these LMBs. And this is why that 18 dB boost is important, because with those LMBs, you can still get good signals. So the idea is we will fly it's still a UAV, but it's not your typical UAV. It's a high altitude balloon, and the idea is to fly it up to 25,000 meters above ground. So this actually work will appear in a conference in Daytona Beach in December called YC. I've never been there, but I thought, well, this conference is made for this kind of work. It's called IEEE Conference on Wireless for Space and Extreme Environments. So let me show you a video of, it is an extreme environment. So this is how it started: Icarus, Stratospheric, Starlink navigation. This is our building. That's Will, who's really the hero of this whole campaign. This is just the beginnings of the payload development. This is a good old styrofoam. If you tailgate, then this will bring some good memories. So, but obviously we don't have beer in there, but instead we put the antennas on top. We have this crazy battery pack to power up our data collection, our inertial navigation system, GPS, and all that stuff. We did some driving tests in Ohio State, and then we ended up going from Columbus, Ohio, all the way to New Mexico. That's where we flew with the help of Sandia National Labs, to whom we are extremely appreciative. So that's the day of the launch. You see here preparing the payload. That's the balloon getting helium. They are testing it. We thought they are more sophisticated how they test it. They're like, oh, this looks good. Okay. So if you are from Ohio, this is the OHIO. There were only 4 from Ohio State. So we used the balloon as the 4th, doing some push-ups. They shut down the runway of the air. And then that was really devastating. So we ended up simulating everything. No, I'm kidding. Let's try again. It took us about a month to recover the payload. Thankfully, it immediately fell. You can see also a new launch team now that we told them, okay, we want someone that. Okay, so took off, ultimate balloon launch. Let's go balloon retrieval. So it ended up flying for, this is the entire trajectory, 65 miles, 105 kilometers. Then Will and his buddy went on private ranches, went on government land. It was just to retrieve the balloon. Finally, they found it, and here you go. That's the balloon. After it popped, came down, and now we started processing the data. So let me show you. The fun thing is we managed to get Starlink signals. We even managed to track them. This is also the carrier. Actually, interestingly here, as you go higher, your carrier to noise ratio will get higher because you are getting closer. So you can track a bunch of satellites at 82,000 feet. This is the ground truth in blue. We had the GPS receiver on board. The open loop, so without GPS, just based on a dynamical model, is in red. And in green is the LEO plus altimeter. So altimeter data plus LEO signals from Starlink, about a kilometer trajectory, and then position RMSE was about 12 meters. And this is just very, very fresh. I mean, hopefully things as we process and improve our design will get better. So let me talk a bit about how we can estimate clocks of these LEO satellites. So adaptive estimation of clocks. I told you earlier, GNSS or GPS satellites have atomic clocks. This is a picture of an atomic clock. I was at Aerospace Corporation in LA some time ago, and then they told me, actually, we have a clock, one of the atomic clocks, in one of our rooms. And I asked them how much, and they said upwards of $1 million. So, but I can tell you those Iridium, Starlink, Orbcomm, these satellites don't put atomic clocks. I mean, they launch them like by the dozen, like you're in Costco. They just send a bunch. So the question is, what clocks, what's the stability of the clock, and how can we estimate it? I'll not go through this here, but this is a standard estimation problem pioneered by a number of researchers. One of the most famous ones is Bar Shalom. It's called the interacting multiple model filter. So we applied the IMM, interacting multiple model, to estimate the clock stability of these satellites. And the idea is we will make things as constant as possible. We will use Orbcomm satellites. So Orbcomm tells you where it is. They actually, in their signal, they transmit their position. So if we decode those bits, we know where Orbcomm is. And we will try to estimate now Orbcomm's timing error, our timing error, and our position. So that's the setup of the problem. The idea behind this IMM that we designed is as follows. So if you are familiar with estimation or the Kalman filter, right? You have your Q matrix, the process noise covariance. You don't know that. Of course, in simulation, you're always right. You set your process noise covariance and you feel good about yourself. In reality, you don't know. So what do you do? As a designer, you can be one of two things. You can either be very conservative. You say, okay, I think Q is very large, which corresponds to bad clocks. Or you can be optimistic. You can say, okay, Q is going to be small, which means that those satellites have good clocks. So those are the two. You use your best guess of the physics. Or you can do an adaptive filter, which estimates that Q for you in real time. So the way we set it up is we said, let's do this adaptive filter, and we will compare it to a conservative versus an optimistic filter. So what you are seeing here are the results. Let me zoom on them. So by the way, it's a single Orbcomm satellite that flew. This is our initial estimate. This is the 99th percentile uncertainty. This is really where we were, and we tried to estimate ourselves with these three filters. So if you look, first, let's look at the conservative. It did fine. This is the uncertainty in yellow, and it converged here, not too far. The optimistic was, the scary thing about it is it was inconsistent. It was so sure of itself, it was inconsistent. And finally, the adaptive is in cyan or in blue. It got here. That's the interacting multiple model. So if you compare them, the optimistic was 429 meters off. This was 254. This was 111. So that's with a single satellite. Okay, so if you are interested, there is a paper we published in IEEE Vehicular Technology Conference in 2023. So this is just so, I don't have any machine learning yet. I will just put it in there. This is a side project I did. I'm more of a model-based person. You can take it, you either like it or you don't, that's fine. So the idea is let's use some machine learning. So how we need some data sets to train on. So the idea is, okay, how can we estimate the satellite ephemeris? I told you that's something we need to refine. We have a good starting point, but we need to refine it. So the setup we put is, okay, imagine you have a tracker. It knows where it is. It listens to a satellite as it flies over, okay? And it tracks the satellite. So if you use your best knowledge of the satellite based on TLE files, and then you propagate them through something called SGP4, Simplified General Perturbations 4. That's an open loop propagator that starts with an initial estimate and propagates the satellite for you. You will get that at. But really, the satellite is the blue trajectory, which you don't know. So if you have a tracker, you can do closed loop tracking based on Doppler or pseudo range measurements you make, and you can refine your estimate, right, of the satellite's trajectory. And then you can give it to a neural network and tell it, okay, predict to me when the satellite comes back, I want to navigate with this bad boy, right? You tell me where it is. Otherwise, which is definitely better than doing open loop propagation. So we put this into test. This is the navigation filter setup. It's a tightly coupled LEO-aided inertial navigation system. I'll skip through it. If you want more information, we just had a paper in IEEE Aerospace and Electronic Systems magazine that talks about this approach. So we listened to 2 Orbcomm satellites that flew over us. You can see here the time in UTC, around 1 a.m. UTC time. Then we trained our neural network. When they came back, it was about 3 a.m. UTC time. We navigated with them. So let me play a video of this. So that's our location. So this data set was when we were still in UC Irvine. So we listened to 2 Orbcomm satellites and we tracked them. So if you use this SGP4 business, right, and TLE, which is the public knowledge, the open loop, you are about 1.8 kilometers in error. Whereas if you track them, you bring it down to 278. So that's why, and you need obviously data that's closer to ground truth to train your neural network on. So that's now the training the satellite's leave view. So we take our open loop propagation and we take our tracked ephemeris and we tell the neural network, learn the errors in the open loop propagation. So when the satellites come back, you tell us where they are. So now the satellite came back. So we navigated the vehicle. You will see here in a second. We just gave the vehicle its initial estimate. So we told it, this is where your position, this is your velocity, and this is your time. And from this point onwards, navigate with these Orbcomm satellite signals. For the Orbcomm satellite's positions, we ask the neural network. So that's what you are getting in green. And blue is the ground truth. So this is driving on the runway, on the highway. And red, don't even look at it. This is the INS with no GPS. It just drifts away. And that's what happened to our aircraft. And in pink, this is based on SGP4. So because of its errors, it is off. And the idea is how can we reduce that? So we ended up driving for about 4 kilometers, 175 position RMSE meters with SGP4, and we brought it down to 18 there. So I talked about radio slam. So I think of Stan. Can I go a few more minutes? Okay, perfect. So we talked about radio slam, and with the help of my students, Joe and Joshua, we were sitting one night, I think it's 10 or 11 a.m., trying to come up with a new name for this. Because now we are going to satellites, radio slam doesn't exactly apply. So after a few iterations, we called it STAN, simultaneous tracking and navigation. So this is radio slam with a moving object, with a moving transmitter, which is the satellite. So this work appeared first on the cover of Inside GNSS and magazine in 2019. And the idea is, instead of only estimating the states of the transmitter, which is its position, it's not moving. If you have a satellite, you have to estimate its position and velocity. And you still, of course, have to estimate its timing error. It is really, really a hard estimation problem. So we've been working on this idea of STAN for some time. I will skip the details here. You know, we have a dynamical model for the LEO. It turns out a two-body with J2 perturbations is good enough to capture. We do, but we will now simultaneously estimate in our filter the states, not using a machine learning approach, but using the dynamics of the satellite. So we'll augment our state vector with the states of all satellites in view. So I'll skip through this. So that's STAN. That's the idea behind STAN. And then we evolved STAN more, and we said, well, you know, I'll skip this. Okay. So we said this is SGP4. So this is what you can do today. You don't have to worry about the satellite states. You can use the whatever publicly available to tell you where they are. This is STAN. Let's estimate the satellite states simultaneously. Then in navigation, there is something called differential navigation. This is what allows your GPS receiver to get to decimeter level or centimeter level accuracy. The idea is you have a base station listening to the same satellites, and it sends you differential corrections. So what if and it's known to either eliminate common mode errors or reduce their effect significantly. So they will reduce the effect of the satellite ephemeris error significantly. So that's differential. Or you can do DSTAN, differential simultaneous tracking. So you have a base station and you still estimate. So let's see how well you can do with all of these. I'll skip this. This is just the setup. So Ohio State has an airport. We decided, okay, let's imagine we will fly an aircraft from that airport one day. And we will use, you know, different constellations to see how well we can do. Let's say we are in the world where Starlink is fully deployed, so you will get 88 Starlink satellite signals, 22 OneWeb, 1 Orbcomm, Iridium, and Global Star are not launching more satellites, so you will get, you know, a couple if you are lucky at a time. So this video shows you an aircraft navigating with these different frameworks to see how well you can do. So ground truth is in blue. SGP4 LEO starts off, and then the errors are so much, it just diverges. Then you see STAN is doing well, differential is doing well, and DSTAN is doing well. It's very hard from this figure to see, you know, who's the winner. I always like to have some rank ordering. So let's see. So if you use, I call them the old club, which is the older constellation, 1 Orbcomm, 2 Iridium, 3 Global Star. I'm not showing you the SGP4. The errors are so long, they're not even worth looking at. STAN is doing well. You know, 15 meters position RMSE. Differential is better, but you will need a base station. And DSTAN is better. Let's go to OneWeb, the same thing. Let's go to Starlink. And to be fair to OneWeb, I'm going to use the same number of satellites as in Starlink, so 22 and 22. Starlink happens to have better geometry. OneWeb, you know, their orbits go north, south, whereas Starlink has several shells. So it's a better design for navigation, at least. Now, if you get greedy and you say, I'm going to do all of Starlink, this is interesting. Differential cannot continue to correct the errors as you think. And it has to do with how the errors get projected into the satellite along track, cross track, and radial. So we managed to find a theoretical reason why as you use more, it's not necessarily better. So differential cannot correct all the errors for you. Now, if you use all constellations together, you see the same thing. So we put this onto a real experiment, real vehicle, and we saw a similar behavior. So you see here, you know, different trajectories. This is GNSS INS. This is the LEO based on SGP4. If you use STAN is just predictable, differential is good, and then differential STAN is the best. I will fly through this real quick. Since then, two of my students have been studying the ephemeris error more from an orbital mechanics point of view and projecting the spatial. You have two error sources that show up additively in your signal. It's a spatial error and a temporal error. So how can you disambiguate them? What can you do? So this is really recent work. We just published it in ION GNSS conference. This is applying it on a real vehicle. I think this is the most accurate navigation results with LEO to date by correcting these spatial errors in real time. But I really enjoy this work as well. I will end here. And the idea is, imagine you have a base that you position very, very far away. And I'll show you how far in a second. It's listening to satellites. And my student managed to boil down the significant errors in ephemeris to 2 parameters. And I didn't believe him when he told me the idea. And then when I saw the math and I started warming up to the idea. But really, 2 parameters suck up most of your ephemeris errors. Now you have to deal with a temporal error. He came up with a theorem that proved that there is a point in time during the satellite trajectory where the temporal error and spatial error get decoupled. So the idea is you listen to the satellite as it moves. What you are measuring on that satellite is a pseudo range. It's composed of the range, the orbit error, and the clock error, but they are all, added up, and there is, terms under the norm and so forth. As the satellite moves, it gets to this time t star, at which your orbit error disappears. So you only have your predicted error and your clock. You disambiguate time from space. Then you estimate these 2 parameters called kappa and ER. As the satellite moves, you can send these 2 correction parameters to a navigator and tell the navigator, correct the spatiotemporal error with them. And we joke that you can even text them to the navigator, and we can place the navigator very, very far. So you can ask me, well, how far are you going to place them? So Ohio is known as the birthplace of aviation, right? So I told them we are going to go from the birthplace of aviation to the birthplace of Starlink, position, navigation, and timing. So it happens that conference in 2019 was in St. Louis, so I call it the birthplace of Starlink navigation. So we set up our reference receiver in St. Louis, 635 kilometers away from Columbus. He happened to be driving back from the balloon experiment, passing through St. Louis. So I thought, okay, camp there, listen to Starlink satellites, correct these 2 parameters, and send them to Joe, who is in Columbus. So that's him actually in a Wendy's parking lot collecting the signals. You can see it in his car. Send these 2 parameters to Columbus. We will track the satellites, and we will see how well we can do. So also, Will happens to be a fan of LeBron James, who's from Akron. So we said, okay, let's start our estimate 200 kilometers away in Akron. We will listen to the satellites as they fly over, and we will correct them, and we will try to localize ourselves. And when we did this, we started with initial, by the way, if you use SGP4, those uncertain, you do converge, but to 2.41 kilometers. And if you use the technique that he's been building, it's 8.78 meters. So that's a causal correction compared to what I showed earlier, which is a non-causal correction. So with that, I thank ONR, AFOSR, Department of Transportation, NSF, Aerospace Corporation, and Edwards Air Force Base, and I thank you for your patience.
It's tall.
Well, I appreciate the comment. And yeah, I don't run away from modeling. I think modeling engineers are the most important, more in my opinion than design engineers, because you can design all you want. If you have a bad model, And because I had a short stint in industry, I learned it that way. My first project, my boss gave me, a controller design, and I went to him foolishly asking him, well, what's the plant model? He laughed. He said, go figure it out. If I know the plant model, why should I hire you? So, what I'm saying is you don't start with assume or given this model, given the Q and R matrices, if you're doing an estimation problem, given this estimate, given this uncertainty, you have to figure it out. So this is why I push myself out of the comfort zone of theory and simulations alone to the real world, because the real world it becomes a cyclical loop, right? So your experiments will illuminate what models are good or bad, how much, all models are incorrect, but some models are useful. So when you're an engineer also at that, so you want a good enough model to use and not complicate things just for the sake of complicating it. Showing you, extended Kalman filter can do a lot of great work. Can you do better? Of course you can do better, but is it worth the computational cost? Is it worth the effort? And maybe it is. Depends on your application. But I would definitely encourage you, take yourself out of your comfort zone to the real world. Because then you are solving a real problem, not a simulated problem.
Increasing the number of base stations would increase the accuracy of your analysis.
Absolutely. Absolutely. Then that opens up another research question, is how many base stations and where? Yeah, there is also a trade-off. It's will improve at one point. You will get little payoff, but that's a very good insight.
Formative and fun. We heard lots of stories about how and very inspiring from how hands-on you are, but at the same time being very technically deep and developing these theories. These are topics that are quite far away from the ones that I regularly think about. So I want to ask, at some point in the middle, you spoke about how there's the possibility of setting up the LEO constellation to be dual purpose versus single purpose versus purely opportunistic. And I wonder, what are the pros and cons of setting them up in one of those? Are there resource costs involved for a provider who's setting up one of these constellations if they want it to be deliberately designed to be dual purpose?
Yeah, great question, Dinesh. So let's talk about the dedicated first. So dedicated, these things are not cheap. This is not a Roomba that you are putting in your home. You are setting up a constellation of satellites. So building the constellation, launching the constellation, maintaining the constellation is one. Decommissioning the satellites, hopefully we don't turn space into space junk like we did for Earth, and then it's unusable for generations to come. So how do you deactivate the satellites? That's another concern. And a big one as well is the spectrum that you're going to dedicate. That bleeds into the second. The second, I think, is more, I would say, digestible, which is dual purpose. But still the spectrum issue is there. Spectrum, you have to dedicate, because you're transmitting another signal. Now, how do you transmit it and so on? There are some, I would say, advantages for being opportunistic that the dual purpose doesn't offer, which is one, you don't pay a dime. You can use the satellites, you don't pay them, right? Two, you maintain your privacy, because once you are using the dual purpose, it could be the case that you're also communicating back, so they know where you are, right? So that's also, in cell phone-based positioning, there is a signal called PRS, positioning reference signal. It's in the protocol. But if you use it, first of all, you're only using towers from your provider. So if you are AT&T, you're using AT&T, whereas in my case, I used AT&T, Verizon, T-Mobile. So now you're using AT&T, and the AT&T towers know where you are very precisely because it's a two-way communication. And so there are advantages for the opportunistic that the others do not offer. I'm more concerned with space junk. And if we have things why do we want to be wasteful? If we, why do we dedicate more spectrum? Why do we want to build a new system? Just because there are lobbyists that want to pay for it, right? And really, this is the truth of the matter. That's what it's coming down to.
Most amazing talks I have seen in the GRASS seminar, so I really appreciate it.
That's humbling.
What have you ever tried these kind of systems in highly remote environments such as New York City? If you did, what are your results? My second question is it possible that these companies will design adversarial features to is open? Thank you.
Well, those are really deep and good questions. First of all, I'm humbled by your comments, so thank you very much. Let me talk about the first one. Multipath is a problem that has been and continues to be studied by the community. If I had given my other talk, which is on, by the way, on the distinguished lecture, I gave it last year. It focuses on terrestrial. I do have several papers that looked at multipath mitigation, but at a very high level. Multipath, yes, is an issue. How do you mitigate it? The schools of thought can be as follows. One is at the receiver level. So the receiver has mitigation algorithms, one that we developed called, it's based on CFAR, constant false alarm rate. So basically what happens is you have a line of sight peak and then you have a non-line of sight peak. And if your receiver locks to the non-line of sight peak, that introduces ranging error. So that's the issue with multipath. Now you're attacking the multipath instead of the line of sight from the transmitter. So that's one way to mitigate it. And we've had papers and others in the community. So that's your first line of defense. The second line of defense that we worked on is post-receiver. So you get a measurement. It is probably corrupted. How do you correct for those? So now you have to think of short-term multipath and short delay multipath and long delay multipath. So the way we had done it is with multiple antennas. So you can have physical antennas, antenna arrays. So now you are adding direction of arrival, or you can have synthetic antenna array. So as you move, you synthesize an antenna array. Of course, you can't do it infinitely because the channel has to be stable enough and coherence and all that come into play. But the idea is as follows. Think of beamforming, right? So if you have a multipath and you know where you have a good estimate of where you are initially and where the tower is, and then you have multipath components, you can beamform at towards the line of sight and null the non-line of sight. And as you move, you continue this process, always beamforming. That's your second line of defense. Now, the third line of defense, I call them, and this is just my own terminology, so you can laugh at me if you want. The third line is at the estimator line. So in the navigation world, there is a notion called integrity. So integrity at a high level tells you, and it's used a lot in aviation, it tells you, think of a bounding cylinder or a bounding box around the aircraft. It tells you, look, I guarantee that you are, or the aircraft, so that's centered at the estimate, but the real aircraft is within this box with this probability. And then they start specifying protection levels, horizontal protection level, vertical protection level, alert limit, because at one point you can go to the user and tell him or her, look, I cannot guarantee this positioning anymore. So what these do is they do something called, very similar to fault detection, isolation, and recovery. You have a faulty signal, probably it has multipath that wasn't mitigated through these two lines of defenses. You detect which signal it is, you know which one, and you exclude it. You say, the hell with it. Because otherwise I will be, if I add it, I will contaminate my estimate. That's the answer to your first question. And that's something, being studied extensively. I kind of moved away from it in the past couple of years. This for the second question. That's an interesting cat and mouse game. Let them do it. Let them do it. Let's see if we can still. Well, yeah, we'll guarantee a job security, I guess.
Yeah, one thing is that if you want to talk, you're gonna have pizza lunch and then.
Please come and ask more questions. Of course, we'd love to continue keep running this, but I think we're probably going to get kicked out of the room soon, so we need to stop. But
Thanks,
so
Dinesh.
once again, Zach, for the really inspiring talk. I have been asked to point out also that we are going to have another last seminar talk next Friday, October 25th at 10:30 a.m. once more. This time from Ruslan Sarakutinov at Carnegie Mellon. And so for more information on upcoming events, be sure to follow us on social media or check out the website. Thank you again.